So 10.4, integral test for convergence. So our objective today is we're going to be covering the integral test for convergence, and what we want to focus on is that there are three conditions that must be satisfied in order for us to apply the test. So we're going to be looking at those three conditions. We're going to be checking how we can make sure that they're satisfied. Once we are certain that they're satisfied and we can apply the test, then we'll apply the test. Okay? So what is the test? Well, here you go. Integral test for convergence. So yesterday's was the test for divergence. Today's test is for convergence. And actually it can be both. It can either converge or diverge. So they call it the integral test for convergence. That's actually, the name integral test for convergence is from College Board. That's what they call it. As you can see, this is from the book, a screenshot from the book. The book just calls it the integral test. So, because it can actually show both convergence and divergence. All right, so I'm going to go ahead and start going over this test and kind of what it means and what we have in here. So it says, if our function f is positive, continuous, and decreasing for x values greater than or equal to 1, and a sub n is equivalent to f of n, then the infinite series of a sub n and the improper integral of f of x, so 1 to infinity, either both converge or both diverge. So this is where I was saying that we're going to take a jolt down memory lane. We're going to go back to our improper integrals. We're going to use those to help us determine convergence or divergence of the series. Okay? Now, my note down there. Note that there are three conditions that must be satisfied in order to apply this test. F of x must be positive, continuous, and decreasing eventually. So, why did I put in that eventually? So that means that I could have a function, let's say a function, and remember we're looking from 1 greater than or equal to 1, right? So I could have some function that is increasing, but what is important is that at some point it goes decreasing, and it is decreasing from that point forward, okay? So I could have some value, let's say, maybe call it m, that's an interesting m. That m has to be greater than or equal to 1, and for that m, as long as all the x values beyond that to infinity, we have a decreasing function, then we can apply the test. So it doesn't have to be that we are decreasing from 1 on. It just has to be that we are decreasing from some point greater than 1 and onward. Okay? So that's why I'm saying that it has to be decreasing eventually. And it needs to be decreasing from that point forward. Okay?
Why does the theorem write it as if it's
That's the way they wrote it. And so for that reason, actually, if you look at the video from College Board that they have on there, the guy that does it, he changes the way it's worded a little bit. He actually adds in, like right here, he says, if f is positive, continuous, and decreasing, for x greater than or equal to m, where m is greater than or equal to 1, and so he adds in that so that it kind of takes care of that we need to have some value of m, that x, everything beyond that value we are decreasing.
Could it be negative as well?
No, so it always needs to be positive.
It always needs to be positive, it always needs to be continuous.
Exactly, yes.
The only exception for the m value
is the decreasing. It needs to be decreasing eventually, yes. Okay? Okay? But I chose to use the books because I thought it was a little bit more concise, and then I would just kind of explain the whole eventually concept there. Okay? So let's go ahead and look at a problem. Let's look at this one here and just kind of see how we can. So there are two parts. We first need to confirm whether the integral test can be applied, and then if it can, we want to determine convergence or divergence. Okay? But we need to determine if it can be applied first. So what are the three conditions that we need to test? Continuity. So let's just look at that one. Is this continuous? Are we going to have any discontinuities for values greater than 1? This actually has no discontinuities at all, right? Because of the n squared plus 1. So this is definitely continuous, so we're good there, right? Let's see, positive. Is this going to be positive? So remember, we're looking for n is greater than or equal to 1. So for all values n greater than or equal to 1, is this going to be positive? Yes. All right, now we look at decreasing. How can we figure out if it is decreasing? The derivative. So let's go ahead and look at the derivative. So we'll say f of x is x over x squared plus 1. And let's go ahead and look at the derivative. So what would that require? Our quotient rule, right? All right, so let's see. Low d high minus high d low over low low, right? All right, so let's go ahead and simplify that. So we have, let's see, I'll go ahead and bring that to the top, actually. So we have x squared plus 1 minus 2x squared, right? Does that look correct? Over x squared plus 1 squared. So I should have negative x squared plus 1. So I need to look at critical points. Is the denominator going to give me any critical points? I can't set that equal to 0 and get anything, right? The denominator. So we're just going to look at the numerator. So I have x squared equal to positive 1, right? So where do we have our critical points? Plus or minus 1, right? But we, again, are only really concerned for x values greater than or equal to 1. So if we are to look at the full interval, right, we would have -1 and positive 1. And back when we were really looking at decrease and increase, and we would look at all three. But do we care about these two intervals? No. So we only need to test this interval. So let's pick a value. Let's say 2. Okay, so we need to know, is that going to give us something that is positive or negative? We want decreasing, so we want it to be negative. Is that going to be negative? Yes, right? Because if I try that out, f prime of 2 would be -4 plus 1 over, that's always going to be positive. So yeah, that's going to be a negative over positive. So that is going to be negative. So are we decreasing for x greater than or equal to 1? Yes. So can we apply our test? So we can say yes, the integral test can apply. All that work, does it tell us anything about convergence or divergence yet? That's just to tell us, can we actually even use the test, right? So now we need to actually apply the test. So remember, what did the test say? If those three conditions are met, what can we say? Looking at these two either both converge or diverge. So now we are going to look at our improper integral. If we can show that that converges or diverges, then the series converges or diverges. Now, how do we find the improper integral? Do we remember? So let's set that up. Integral from 1 to infinity of our function, x over x squared plus 1. How do we go about doing that? Mm-hmm. And we do the limit, right? So we're going to say b goes to infinity of the integral from 1 to b of x over x squared plus 1. Looks like I have a u sub that I can use, right? So I should be able to say that that is the limit as b goes to infinity. U sub would be x squared plus 1. So I should have a 1/2, right? 1/2 of the integral from 1 to b of 1 over u. Does that look right? Does that look correct? Okay. And 1 over u is the natural log. So then that becomes the limit as b goes to infinity of 1/2 of the natural log of u, but I'm going to go ahead and just put my u back in, so that's x squared plus 1. And then that's going to be going from 1 to b. All right, so that's going to be the limit as b goes to infinity of 1/2 of the natural log of b squared plus 1, right? Minus the natural log of 2. Okay, so then let's think, if we plug in infinity, do we converge to a value? So is this converging to a value, or is this unbounded and going off to infinity? It is unbounded. If we think about the natural log function, that is definitely going to be increasing without bound. And so this part here is going to infinity, right? The other one, it goes to 1/2 natural log of 2, but that one goes to infinity. So this diverges, okay? So the integral, and let's actually just write the integral. So the integral from 1 to infinity of x over x squared plus 1 dx diverges. Now, what does that tell us about the original series then? That also diverges. So we can go back and now say that this original series also diverges. Okay? And that is the integral test. You would want to state out the theorem, yeah. You would want to say, hey, my limit, or the integral diverges, so my series diverges. Yes?
So you can put down either infinity or negative infinity as a result of a limit. So I just say that limit on the bottom line, like all the way to the right, equals infinity first, just so they know that that's true.
Yeah. Yeah, so let's go ahead and do that. That equals infinity. There we go. Kind of had that implied here, but it's not a bad idea to put it there as well. All right, so this is not necessarily going to be your favorite test. Okay, we will see other tests that might be more useful for us, but this is one that can be applied, and it's one we're going to add to our arsenal of convergent and divergent tests. Okay? All right, so let's go ahead and try another one. I want you to try this one. Go ahead and tackle it and see what you can do. Okay, so remember I said that for the decreasing, it has to be decreasing eventually. It's eventually for all three. Okay, so it's eventually, as long as eventually you're always continuous, always positive, and always decreasing. Okay? All right, so let's go ahead and start looking at what's our first criterion. Continuous, positive, and decreasing, right? So let's look at continuity. Do we have any discontinuities? Will that ever equal 0?
Are you asking the
Yeah,
denominator?
so at 5 over 2, right? Which is 2.5. Okay, so it has a discontinuity, but that's the only one, right? So we can pick a value greater than that. Let's look at n equals 3. We can say that it is continuous for x is greater than or equal to 3, right? If we pick a value at some point, then we're always going to be continuous after that point, right? Does that make sense? Okay. So that one is good. We have that continuity for some value greater than 1 and beyond. Okay. Now let's look at continuous positive, right? So since I picked the x is greater than or equal to 3, let's go ahead and just check, is it positive for x values greater than or equal to 3? Should be, right? Because if I do the square root, that'd be 2 times 3 is 6 minus 5. That's going to be positive, and everything on is going to be positive. And a square root can't be negative, right?
It's going to exist for the timer. It's -5. Like if you do like x equals 2, it will. There isn't a point there. Is that what 2.5 is?
So 2.5, the actual domain for this would be that it has to, our domain for this function is from 2.5 and beyond, right? We can't have any values less than 2.5 because then we would have a negative inside our square root and that wouldn't work. So it is positive for all values greater than or equal to 3. So then let's go ahead and check decreasing. So we want to go ahead and look at our derivative. Has anybody found the derivative yet? It is ugly. That's okay. So f prime is going to be square root of 2n minus 5 times 1 minus, oh, I should have an x in here, right? Minus 5. So let's see. Times 2. Should just be 2, right? Oh, got it. You're saying 2x and then you put the x afterwards with the chain rule. Got it. Okay. Yes, I understand. And then times 2, right? There we go. Times 1/2. Okay, yep. Got it. So let me actually just write that. That'd be, so 1/2 in front, and then 2, and then that will cancel. Okay, so we have everything there. All right, and then in the bottom, that's going to be that squared, so that just results in 2x minus 5, right? Okay, so let's see. I have the square root of 2x minus 5, and that's going to be minus x over the square root of 2x minus 5, correct? Over 2x minus 5. I'm just going to simplify this because I think it will simplify down okay. So that's going to be 2x minus 5 over the square root of 2x minus 5 minus x over the square root of 2x minus 5 over 2x minus 5. Okay. What was that? Okay. So that should just leave me with x minus 5 over the, let's go ahead and write it. I'm going to do this one here, 2x minus 5 times the square root of 2x minus 5. Okay. Now we need to know when is this going to be decreasing, if it's decreasing. So let's look at our critical points, right? So let's see. We have x equals 5 from the numerator, right? And the denominator is only going to be equal to 0 at 2.5, right? What was that? I don't think it's 0. And also we can't plug in 0 because of the square root. It's not in the domain. So let's go ahead and look at those intervals. We are really concerning ourselves again with x is greater than or equal to 3. But let's go ahead and look at this. So we have 2.5 and then 5. So we have these two intervals here. So let's go ahead and look at that. What's a good value to plug in here? Well, we want to know, okay, well, if you want to start at 5, but it has to kind of match what we were doing over here as well. That's true, right? And that can actually hold true for these other ones as well if we change it to just x is greater than or equal to 5. So, okay, let's just check 5 then. I think that should be fine. So let's pick 6, okay? Because we know this is going to be our last interval from this way, right? So let's check 6. All right, so if I do 6, the top is negative, right? Bottom would be a positive times a positive. So what's my result? Wait, no. Top is positive, thank you. Positive, and this is positive times positive, so I have a positive. So what's happening? It is increasing. So all that work, can we even apply the test?
No.
Man. Test cannot apply. Yes.
Can you go over how you went from the second line to the third line? For the decrease? Second.
Here to here?
Yeah.
So I got a common denominator. So So I said, let me just zoom back in here. So I said this was over 1. I wanted a common denominator, so I multiplied top and bottom by that denominator. So add 2x minus 5 to top and bottom.
Oh.
And the radicals cancel each other out because they're the same, right? Does that make sense?
Yeah.
Mm-hmm. All right. There we go. Okay, let's go ahead and try a little bit easier one. So yes, so we're going to have more tests next week. And so this one, we can't use this test. So we'd have to look at a different test. That's a good question. We'll talk about it. Sometimes they'll also tell you the test they want to see. They'll say, hey, use this test.
Yeah, that's helpful.
Yeah. Okay, let's try this one, guys. First off, see if it can be applied. If it can, see if it converges or diverges. Let's go ahead and look at this one. So it needs to be positive. Wait, yeah, continuous positive and decreasing, right? So is this always going to be continuous?
Yep.
Yes, there's no discontinuity, so continuous. That's good. Positive, is this always positive? That is also, yes, positive. That's good. Is it decreasing? It is. Do we need to see how that is? Or are we good? Okay, and I'm going to go ahead and move on to so this one we can apply the test. So let's go ahead and look at the improper integral. All right, so this is, what am I doing? Okay, so we're doing the integral from 1 to infinity of 1 over n squared plus 1, or let's change that to x dx. So that equals the limit as b goes to infinity of the integral from 1 to b. What am I going to use for my antiderivative here? Arctan, right? So that's just going to be the limit as b goes to infinity of arc tangent of just x, right? From 1 to b. All right, so the limit as b goes to infinity of arctan of b minus arctan of 1. All right, what happens as we go to infinity? What does arctangent do? Do we know? It doesn't oscillate. It has two horizontal asymptotes, positive pi over 2 and negative pi over 2. And it goes, if I can draw it, like this. So what happens as we go to infinity? What does it reach? Not infinity. It equals pi over 2. And then what is arctan of 1? Pi over 4. So that's just equal to pi over 2, right? Oh, wait, no, yeah, pi over 4, right? Yes, pi over 4. There we go. So this converges, all right? So we can say our statement would be, since this of 1 over x squared plus 1 dx converges, then the series from n equals 1 to infinity of 1 over n squared plus 1 converges. Now, what you have to be careful of, the integral converges to pi over 4. That does not necessarily mean the series converges to pi over 4. You have to be careful with that. This is not the sum of the series. Okay? So you have to be careful of that. Don't try to say, oh, we got pi over 4. That must be the answer to my original problem. It is not. This is just a test to determine convergence or divergence. It is not to tell us what the actual sum is. Okay? Does that make sense? All right. So we are close to the end, so we'll just go ahead and end there. All right, your homework tonight, you're going to be looking at some integral test situations and practicing this, okay?